Hi, this is Sholey Physics, episode on gravitational potential energy and escape velocity. We're going to be looking at conservation of energy along with gravity, but from the universal gravitation perspective to figure out what speed we need to just get away. You ever feel like you just want to get away? Well, to get away from Earth, you need a certain escape velocity. To get away from the sun, if we're going to go, extrasolar, get out of this solar system, we need a particular escape velocity. And that's what we can determine with conservation of energy concepts. Now, take a little step back. I mentioned needing universal gravitation to figure this out. Back in the energy unit, you may have explored gravitational potential energy of an object near the surface of the Earth based on the work kinetic energy theorem. And that's just where you get work for lifting an object up is force times displacement, but in the vertical sense, the force is the weight and displacement is the height. So you got used to using gravitational potential energy as mgh. You do keep in mind that this g is 9.8 meters per second squared, being near the surface of the Earth, and of course this changes as you get to a significant altitude above the surface of the planet. So we need to transition back to Universal Gravitation Law if we're going to leave the Earth forever. Forever. Okay, so we need to explore escape velocity. Now, if we're to lift a spacecraft up off the surface of the planet, all right, we're going to need to do some work. And you might recall that work is integral of f of x dx when it comes to a force function that changes with displacement. Our displacement in this case is r, so we're going to be more like talking like pirates here. R. We're going to use f as a function of r dr. Okay, and we're going from one height to another, one r position. We might go from the Earth's surface to some position r up above. There's a little bit more to this gravitation law. If we think of it in terms of a vector, of course, that gravity works in the negative r direction. And so there's a negative tag on here. When we take the dot product of f of r dr, we're going to end up with this negative. And that is going to be an important piece to our little piece of a puzzle here. So let's set this up in terms of gravitation law. Integral of f of r dr. Now our force function is g, mass of Earth times the mass of our object divided by radius squared. And we're going to have a dr on the end of this. I'm going to apply the negative just to the front here. It's going to be part of those coefficients. There it is. Now if we integrate that, we have a whole bunch of constants up here with negative g mass of Earth times m. And the integral of r to the negative 2 is we're going to increase that power to a negative 1. So r to the negative 1 is over r. And we would get a negative out of that also. So multiplied by negative 1. Because it's going to be 1 over n plus 1, which is negative 1. We're going to take a look at that evaluate that from radius of the Earth up to r. All right, negative times the negative is a positive, so we're going to have a g m over r, that's our final, minus g m over re. Okay, and what do we see here? Well, if our r value is radius of the Earth is less than the r value here, you'll notice that there's kind of a change. This is going to be a negative change because when you divide by a bigger number, when you divide by a smaller number, you get a bigger value. That's where I was going with that. So here again, we see that work, if we relate that to potential energy, being a negative change in potential energy, change in potential energy is the final minus the initial. Then if we apply this negative in here, what what do we get? We get well, this is the initial over here. If we look at these amounts, we have the final condition at a radius r, and the initial condition here. And sure enough, this would be the work in lifting the rocket up. Therefore, what is the work done by gravity? That would be the potential energy. Work done by gravity would be the negative of that. So therefore, the implication is that if we're to get this UF minus UO to equal a negative UF minus UO, what that means is these values here I have to match up to a potential energy, these values have to be the negative of what the UF is. The U final would have to be a negative G mass of Earth m over r. And the U initial, again up here, would have to match up with being a potential energy source, would have to be a negative G MEM over radius of the Earth. Okay, I hope you kind of see that connection, that if we're to compare this work done to a potential energy involved, there's this negative value involved. Therefore, when we're talking about gravitational potential energy in relation to an object leaving the surface of a planet, or the gravitational potential energy between a star and its planet, or between two objects in space that are significant distances apart, that means potential energy in general is this, G M1 M2 over R. There's that negative value in there. Now this is really important, and this is the only way that potential energy is going to make sense, graphically especially. If we think about a plot of potential energy versus position, R. And I'm going to go ahead and put in an object here that represents Earth. There's our circular object, our planet. That represents Earth. This point represents the radius of the planet, the distance. And that's usually where we're taking off from. Some different things happen on the inside here. You might recall that the force decreases linearly inside of a planet to 0. If you ever did that problem on, reaching the center of the Earth and the force at the center of the Earth. Now the potential energy within the Earth, actually it's kind of a constant, but that's for another day, another time. Right now we're talking about the potential energy. And according to this function, this UG equals negative G, in this case would be mass of Earth times mass of the object that's taking off of Earth over R. This is a function that is proportional. UG is proportional to negative 1 over R. So that's the type of function we need to put in here. And a 1 over R function looks sort of like this, where we've got some asymptotes there, okay? And on this side it looks like that. Not quite as tight for a 1 over R. Therefore, a negative 1 over R function looks sort of like this. This is really important here. Now, inside of Earth, things are a little bit different. So what we're really looking at right here is only this portion of the function. Only this portion. Inside the Earth, dynamics change. Now, this is not a point mass, so it does has some mass surrounding. That's going to change the potential energy within the Earth. But if we look at this potential energy function outside, and if we increase R, look at what's happening to potential energy. You might be like, well, potential energy is negative. That doesn't quite make sense. Well, it does. As R gets bigger, what happens to the value of potential energy? You got to remember, energy is not a vector. This is a scalar. So you got to think of this more like a number line. With a number line, we plot 0 right there in the middle. Everything over here is negative. Everything over here is positive. If R is small, like the radius of the Earth, then we have a negative number divided by a small number. It's a large negative number. It's very negative. It's out here. Now, if R increases, the denominator increases, and I shouldn't say the magnitude. the absolute value, there we go, the absolute value of the potential energy as R increases, the absolute value of potential energy decreases. And that's the important thing here. We're going from a large negative number to a small negative number. So a large negative is here, a smaller negative is here. What kind of change is that? That's a positive change. We're going from a larger negative to a smaller negative. That's a positive change. That's the only way this function can agree with anything resembling the potential energy near the surface of the planet, MGH. We know that as H increases, the potential energy increases also. Well, here, when H increases, that means when height gets greater and greater and greater, that's the same as R increasing. And if you do go from a small r to a big R, our energy function does become more positive and less negative. It's increasing. Remember, there's no absolute zero energy in the universe. You'd have to be infinitely far away from any object in the universe to have zero potential energy from that object. So that's what we're seeing here. As we move further and further and further away from the Earth, the potential energy is approaching zero. All right, if there's zero potential energy, then the object won't fall towards the Earth. And that's where we're going to be going for escape velocity. In order to get away from the Earth, you need to be far enough away where the gravitational potential energy is essentially zero. In other words, R has to be approaching an infinite value so that this denominator divides out the numerator and becomes a very, very small number. That's the perspective we're having here. All right, so in order for a spacecraft to take off the planet and never come back, how much energy does it need? Well, how much potential energy it starts with, we'll say UG initial, is the amount of kinetic energy it's going to need. You see, you've got to lift up the object at least this far energy-wise in order to get up over this, what is that, an asymptote that's approaching zero? That's right. If you bring this potential energy and add kinetic energy to it so that the total energy is zero, then you will have escaped Earth's gravitational pull. You'll have enough energy to get out. And the nice thing about kinetic energy is it's related to velocity. How much velocity do we need to escape Earth? The escape velocity. What's that relate to? The kinetic energy needed to escape. That relates to the spacecraft's starting potential energy on the surface. And that spacecraft's potential energy does depend on the mass involved, where it's starting, and now we know how much fuel we need. Fuel converts to energy. Energy is potential energy needed to overcome, and kinetic energy is how we're going to get there, through velocity, through speed. Here's how it works. Escape velocity. Wow, escape, spelled just like escape. All right, so if we think of our spacecraft here on the surface of the planet, pull out the rocket from my pocket. All right, it's going to be blasting off there. Here's our potential energy curve. It begins with potential energy, gravitational potential energy. Negative G, mass of Earth, mass of our rocket, divided by radius of the Earth. That's where we're starting. And what about out here? What kind of energy will we need out there? Well, if you could launch yourself up off of the planet, eventually the planet would pull you back if you went straight up, okay? And you weren't going fast enough. Important thing. If you launch yourself up higher with more energy, you're going to go up further, but eventually you're going to come back. So, is there a speed at which you can launch yourself upward such that you go so high that you get to the top and you just don't fall back? In other words, can we get to a point where we go so high that our velocity becomes 0 and we don't come back? At an infinite distance away, when r approaches infinity, what does our velocity approach? 0. And if we hit 0 and we never fell back, we've achieved escape velocity. Now, generally, if you did want to escape some kind of planet, you'd go faster than the escape velocity. All right, so you continue on and you go somewhere else. Now, you don't want to just stop. But this would be the escape velocity is that minimum velocity such that you never come back when the velocity is 0. All right. So also at r is equal to infinity, if we consider the generic expression for gravitational potential energy, when r is infinite, what does u approach? Gravitational potential energy also approaches 0 at an infinite distance. And just to further the velocity concept, if our velocity is approaching 0, what is the kinetic energy approaching? 0 also. Kinetic energy is 1/2 mv squared. So at an infinite distance, if we consider energy, and that all the energy in the system is between the rocket and the Earth, and there's no external forces otherwise, the energy in the system initially should equal the energy in the system finally. And what is the energy of the system going to be at an infinite distance? 0. That's what escape velocity is always about, is reaching that 0 final energy. We're trying to start at a potential energy that's negative. I should make it right here. Starting at this negative potential energy, and we're trying to overcome that 0. Something about parenting is there's no escape velocity, and it's always most important to take care of them when they come by. So that was my 7-year-old Jubilee. She was knocking on the door. Anyhow, we need to reach a final energy of 0, and the way we're going to do that by starting at a potential energy down here is adding some kinetic energy that's equal to that amount. So in the initial blast off of our rocket ship, it's going to have a starting gravitational potential energy, and it'll have an initial kinetic energy that we give it. And at infinity, at an infinite distance away, we're going to approach 0. So this is for our minimum escape velocity just to get away. Let's now plug in gravitational potential energy, -g, mass of Earth, mass of our rocket, divided by radius of the Earth. That's where we're starting. So that is right there. There's our amount, radius of the Earth, plus 1/2 mass of the rocket. I'm going to keep it as m to agree with the mass of the rocket over here, times escape velocity squared equals 0. And you see, if we didn't have that negative on front, we'd have a big problem. If both of these were positive and they're both equal to 0, that would be a huge problem right there. There wouldn't be a solution. We'd have to take the imaginary solution, the square root of a negative number. But it is negative, and this is the only way it works. So when we add this to the other side, it becomes an algebraic problem. 1/2 mv escape squared equals positive g, if we add this creature to the other side, mass of Earth times mass of rocket over radius of the Earth. Got some canceling going on, some m's cancel. Bring the 2 up, multiply both sides by 2. Let's take a look. That means the escape velocity would be, these 2's cancel, the square root, we'll have to take the square root of both sides, 2 times g times mass of the planet divided by the radius of the planet. That's it. You know why I like this expression? It looks like something else. It looks like something very similar. If you consider trying to reach a circular orbit through a very, very different method of, taking a force diagram, noticing that gravity is the only force causing a centripetal acceleration. We got out of that the orbital velocity for a circular orbit is square root of g, mass of Earth, or mass of the planet, divided by the radius of the planet. What's the difference between these two? Just a square root. I love that. Escape velocity is root 2 times orbital velocity. That's it. I find that pretty amazing. Delivered from two different methods, conservation of energy here, application of Newton's second law there. Now, of course, they're all related. I'm sure there's multiple ways to solve these, but this is the best one. To solve for the escape velocity, set kinetic plus gravitational potential equal to 0 at an infinite distance. And there it is. Just to sum up, gravity for the last couple of episodes. If you're looking for that escape velocity that we learned about today, that is root of 2 g, mass of the planet, divided by radius of the planet. For the orbital velocity, looks very similar, square root of g, mass of the planet. That is a funky m. Divided by the radius of the planet. So there's a difference between those two. If you're ever looking for an orbital velocity, what am I talking about? An elliptical orbit. I should make a note here. This is for a circular orbit. If you're trying to find some velocities throughout an elliptical orbit, let's say at the closest approach and furthest approach, what you apply there is conservation of angular momentum. That's the big idea. And you get R1 omega 1 equals R2 omega 2. And that's specifically for the closest and farthest distances between the star and the planet that you're looking at. All right, so our elliptical orbits or circular orbits. I guess I should mention the big idea for each of these. The big idea for this one, way to start out, is sum of the forces equals mass, but it's a centripetal acceleration. And gravity is the only net force there. Okay, and the big idea for this one, escape velocity, is like we saw, that the energy at the beginning equals energy at the end, where the energy final is 0, and you would have gravitational plus kinetic energy at launch. Okay, so those are the big ideas for each one. Big ideas are in parentheses, and the application is not. I hope that helps out, and this is the end of the episode.